In biological systems, like in a mammal's body or something like that, the system is buffered to be at a very certain specific pH, right? So, for instance, physiologic pH is around 7.3. We can take a little bit of general chemistry to figure out what the carboxylic acid is going to look like when it's in physiological conditions, right? And that depends on really two things. The extent to which an acid is ionized in solution depends both on the pKa of the acid, so how strong the acid is. Obviously, stronger acids will be more ionized, as well as the pH of the surrounding solution. So remember, we had the ionic products over the reactant here just as Ka. pKa is the negative log of that. So that just rearranges into this equation here that pH is pKa plus log of this ratio, okay? Ratio of the conjugate base over the acid. Okay? So if you know what the pH of the surroundings is and the pKa of the acid is, you can figure out what the ratio of base to acid is of that actual solution. So how much of it has been deprotonated, for instance. So if I have a solution whose pH is the same as the acid's pKa, say I have an acid pKa of 5, and I put it in a solution buffered to pH of 5, pH of 5 equals pKa of 5 plus it has to be log of 1 to 1 because log of 1 is 0. So solution's pH is the same as the pKa. There's a 1-to-1 ratio of acid and conjugate base, meaning right around half of the acid will be ionized. It will be deprotonated. So you'll have a mixture of, for instance, acetic acid and acetate, 1-to-1 if your pH is right at the pKa. If I raise the pH by, say, 1 unit, I make it more basic, what I'm going to do, I'm going to raise the ratio of the conjugate base by a factor of 10. Okay? To get pH equals pKa plus 1, I have to do log of 10 over 1. All right? Log of 10 is just 1. So every pH unit we increase it by increases our conjugate base by a power of 10. Okay? Solution is more basic. We have more of the conjugate base. So if we take pH 2 above the pKa, we get a 100-to-1 ratio. Lowering the pH, a more acidic solution, we increase the acid concentration by a corresponding power of 10. Okay? So each pH unit we're away from the pKa, we're a factor of 10, power of 10, further from the ratio. So if I have acetic acid, pKa 4.76, and that's in physiological pH 7.3, difference at 2.5 pH units. So our surrounding pH is much more basic than the pKa of the acid itself. So 10 to the power of 2.5, essentially to 1. So somewhere between 100 and 1,000 times more of the acetate ion than the acetic acid. Okay? In other words, it'll be almost completely dissociated. So when we have, if we were to produce acetic acid in a biological system, it would immediately be deprotonated. We would have acetate ions, C double bond O, O minus. So that's why in biological systems, even though these carboxylic acids are so important, your biology textbook will refer to them as acetate and citrate and lactate and fumarate and things ending in ate like that, because we're talking about the carboxylate ion. Right? This is acetate that I do right there. Okay? So if I have an acid with a pKa that's up closer to 7, we'll have more of a mixture of dissociated and undissociated. Okay? That'll be important when we talk about amino acids at the end of the course.